All right, so we are back. Something that I wanted to note, first of all, we were just talking about our equilibrium expressions. Those equilibrium expressions, like I said, are on our equation sheet, okay? So we should be able to use this equation sheet to know how to write our equilibrium expressions, okay? So on to our next piece here. We can calculate a few things with our equilibrium constant, okay? So like I said, right, K equals concentrations, products over reactants, that is something that we can calculate, okay? So if we see here, right, let's read this here, our problem. In a certain system at equilibrium, 22.6 grams of NH4Cl is present. The partial pressure of NH3 and HCl are 2.4 and 4.8 atmospheres respectively. Calculate K. So our first thing to do when it says to calculate K, right, we're going to want to write K equals and then write our equilibrium expression. Well, we have NH3 as a gas. That's one of our products. So it's a gas. We're going to write it as a pressure of NH3. And then we'll multiply that by the pressure of HCl, because again, that is a gas. We would then divide it by NH4Cl, but it is a solid, okay? Ammonium chloride is a solid, so that is not going to show up in our equilibrium expression at all, okay? So now, to calculate K, all we have to do is just plug in the numbers, okay? So we're going to put 2.4 atmospheres times 4.8 atmospheres, and that equals 12. Whoops, 2.5. That's what I meant to put, not 12. So whatever, we're slightly off there. Because it should, I have 2.5 as my problem that I'm following here. So that would be K is going to be equal to 12. So are there units for this? Yes, kind of, but not really, okay? So we can kind of ignore units for this one time with our K values. I know, you are so excited. All right, so now let's look at this next system here, okay? So this next system is a little bit more difficult because what it says is that originally a system contains only HI at a pressure of 1 atmosphere at 520 degrees C. The equilibrium partial pressure of H2 is found to be 0.1 atmospheres. So calculate the partial pressure of I2 and the partial pressure of HI at equilibrium, because this pressure up here that is given is not at equilibrium, okay? So what we're going to have to do is we are actually going to build what's called an ice table, okay? An ice or a rice table, okay? Because we're going to actually put our 2 HI at the top there. We're going to put our equilibrium on there, and then H2 plus I2. I didn't make this very large. You may want to make it larger to give yourself space. But initially here, right, it says originally a system contains only HI at a pressure of 1 atmosphere. So our initial pressure of HI is going to be 1.00 atmospheres. Okay? H2 pressure is 0 and I2 pressure is 0 initially. Okay? Then we say, okay, well, we're going to form and get to an equilibrium. The partial pressure of H2 is found to be 0.1 atmospheres. So our equilibrium is 0.1 atmospheres for H2. We have to calculate our other two partial pressures at equilibrium and then calculate K. So our first thing to realize is that our change here, right, we gained H2, that's really kind of plus X, right? That X is, in this case, 0.1, right? We go 0 to 0.1, our change is 0.1. But it gained X. That X is the same amount. So we gained I2 the same amount as we gained H2. So our I2, right, it's because we have our coefficients, right, our stoichiometric coefficients, we gained x there. And then over on the left-hand side, we had to lose HI to be able to form H2. How much? Well, we had to lose 2x. Okay? So in this case now, right, we gained just as much I2 as we gained H2. So our partial pressure from I2 is going to be 0.1 atmospheres. And then the partial pressure for HI, right, it lost twice as much as it gained of the H2 and of the I2. So it lost 2 times 0.1, which would be 0.8 atmospheres. Okay, so now we have our equilibrium pressures. Let's write, now we say, okay, we need to calculate K. So K expression, K equals pressure of product 1, H2, times the pressure of product 2, I2. We don't have any coefficients there, so we don't have to put any numbers on the top. And then over our pressure of HI, and that is going to be squared. So let's then plug in our numbers, right? 0.1 times 0.1 divided by 0.8 squared. If we do that, let me make sure I get my correct number here. If we do that, right, we should get a K value of 0.016, okay? So these ice tables or rice tables are going to become very, very useful for us. We are going to use them all the time, okay? So you guys will want to use this, right? You will want to use this. So all we do for these, right, we have our reaction. We're going to write out what our initial values are, write what our change is, and write what our equilibrium is, okay? That's what our rice table stands for. So we are going to get lots of practice using these, okay? But we can also then start talking about changing things, okay? So we talked a little bit last year about Le Chatelier's principle and Q, okay? We may not remember Q exactly, but we've talked about Le Chatelier's principle. So let's think about that reaction, that system just up above, right? Initially, we had mostly HI, right? Or we had all HI. So initially, really our Q value, which is where we are, was essentially 0 over 1 atmosphere squared, right? So our Q value, we write it the exact same way as we would write our K expression. We would say, well, the pressure of H2 is 0 times the pressure of I2 initially is 0. We're going to divide by the pressure of HI. That's 1. We're going to square that. So our Q value is 0. So in this case, right, we know, well, yes, there is going to be an equilibrium that we're going to end up going to the right. But we can qualitatively say, right, that our Q value is going to be less than K. Which direction did we move? Oh, look at that. That kind of looks like an arrow, right? So K less than Q, or Q less than K, we're going to move to the right, okay? Do you see how I kind of made that an arrow? If Q is less than K, we are going to move towards our products, okay? So Le Chatelier's principle essentially says that when you have a system that's not in equilibrium, right, you apply a stress, the system's going to move towards relieving that stress, okay? It wants to get rid of that stress. So a way for us to kind of remember that and what actually happens is to run from the fat guy, or we fill the hole. Whoops. Wrong hole there. Fill the hole. Okay? So this phrase right here is going to be very useful for us to kind of remember and understand where our equilibrium is going to move. Okay? So we're going to use this to understand and identify where our equilibrium is and how we can get back to that equilibrium. But we are not going to use this when we write and explain and justify our answers. Okay? So let's think back to that system up above. We said, well, there is a hole here where H2 and I2 are 0, right? We are not at equilibrium. So what we would say is that our system is not at equilibrium. H2 and I2 have a lower concentration than they should at equilibrium. Therefore, our system moves to the right, towards our products to produce more products and get to that equilibrium, right? We are not saying, well, there's a hole on the right, we got to fill the hole so our reaction moves towards products. But we are going to run from the fat guy and we are going to fill the hole, right? We just have to kind of use more scientific language to be able to explain our thought process there, okay? So let's again think about our example from before. Same thing, we were at 0.8, 0.1, 0.1. What if HI, just for some reason we added more HI, it increased the pressure to 1 atmosphere, right? Well, we increased it to 1 atmosphere again. We were at 0.8, we moved it up to 1. Now, all of a sudden, okay, there is a fat guy that is HI, right? So we would expect we are going to run from the fat guy, we are going to move towards the right, and we are going to produce some of our products, okay? So we would say, right, we would expect the reaction to move towards the products. Now we need to justify it. So let's justify it using our K and Q values, right? So our K value we had up, or we calculated it up there. Q, right, we're going to say, where are we actually at? So, whoops, Q equals, well, we had 0.1 times 0.1. Those were H2 and I2. We said that that's what those are at. And then, hey, all of a sudden it jumped up to 1. That's going to be squared, right? We're just plugging in our numbers. And when we do that, 0.1 times 0.1 is 0.01. Divided by 1, we're at 0.01. So now we see 0.01 is less than 0.016. This is K is greater than Q. We are going to move to the right, okay? So we would justify our claim or using this calculation here, okay? So we're going to pause and we're going to come back in a sec.